Swayam Prabha. Digital India. Educated India.
Hello and welcome to the course on manufacturing technology theory and practice. Then we have the end milling cutter. This is the end milling cutter, and you can see that the color is different. This color is actually the coating on the tool, which increases the life of the cutter. So, the coatings are made with the titanium carbide, of different kind of carbides, and coating is only about 5 to 10 microns, so that the tool life can be increased. Two lip cutter, there are two lips only, and these cutters are also used popularly in case of milling operation. This is the slitting saw cutter that we have already seen once, saw cutter, and this is a similar one, but diameter is higher. Okay. And those are the indexing plates that you can see here, and these indexing plates, we will show you the use of those indexing plates for making the while cutting the gear. For example, if you are cutting the spar gear, all right, when the spar gear is made, so one spar gear is, one tooth is made, after that there will be another tooth to be milled. So, from one tooth to another tooth, it has to be rotated, the blank has to be rotated. So, how it can be rotated, how much it has to be rotated, that can be defined by the indexing plate, and that indexing plate is attached to the indexing mechanism, and that indexing mechanism will be using for making the helical and the bevel and the spar gear, that will be showing you in a short while. Well, in this display, what you can see is the different kind of mechanisms through which the power can be transmitted. Let us see here, this is the spar gear. This is a mechanism through which the power can be transmitted through the parallel shafts. Let us say these are the two shafts and they are parallel to each other. So, when one shaft is moving, the another shaft is also moved, and the transmission ratio, we call it as the number of teeth, depends on the number of teeth of these two mating gears. For example, if you rotate this, all right, this will be rotated at the faster speed, and if you rotate this, this will be rotated at a slower speed, because then the transmission ratio will be this divided by this. And in this case, this transmission ratio will be this divided by this, so it will be faster, and this probably you will be already knowing that. And these are the two spar gears, and each of these spar gears will be mounted on the shaft which are parallel, which axis of these shafts will be parallel, and the power can be transmitted. Now, this is a positive drive, because there is no slip when the transmission, when the power is transmitted from this shaft, for example, to this shaft, then there is no slip. So, there is a positive transmission. Here if you see the worm and worm wheel, this mechanism called the worm and worm wheel, this is a mechanism which is used for a very low transmission ratio. So, here the transmission ratio can go from up to 1:40. Here, as you have seen, that if we rotate this, this gear will be rotated, and it can be vice versa. So, you can rotate this gear will be rotated. But in this case, what happens is that if you are moving the worm wheel is rotated, but if you move the worm wheel, the worm is not being displaced, not moved. So, therefore, apart from the advantage of having the 1:40 transmission ratio, up to 1:40 transmission ratio, depending on the number of teeth here, another advantage of the worm and worm wheel will be that this is locking mechanism, meaning that if this is the driver, this will be driven, but this cannot be driver in this case. I give you an example of let us say crane. All right. When a crane is lifting a mass or a weight, all right, if power fails in between, had it not been the worm and worm wheel attached there, the weight can be coming down, and you know what is that mass they lift. That can be a concrete block or a full concrete block for a room or something. So, they are very heavy and accident can happen. Or if you have seen the sliding doors, for example, there also the worm and worm wheel mechanism is used. So, that the 1:40 transmission ratio and very high torque carrying capacity can be imparted. So, that is the advantage of this kind of mechanisms. These are the transmission ratio can be as higher as 1:40, and the locking mechanism of the worm and worm wheel, for which these are popularly used. Now, this is a mechanism which is called the rack and pinion mechanism. So, here also if you can see that either you drive the rack, the pinion is driven, or you drive the pinion and the rack is driven. So, this mechanism is normally used for converting the rotary movement of the pinion to the linear movement of the rack, or for converting the linear movement of the rack to the rotary movement of the pinion. Now, here for example, if you have a shaft, on the shaft you can cut a rack like this, and that rack can be engaged with the pinion. All right. So, when the shaft is moving linearly, in that case the pinion will be moving accordingly in the according direction, and the shaft which is mounted along this axis, that will also be rotated. All right. So, this mechanism is once again used for converting the rotary movement to the translatory movement, to the reciprocating movement, and vice versa. All right. And here there is no locking mechanism, as you can see, that both can be a driver. Pinion can be a driver, this can be driven, or the rack can be a driver and the pinion can be driven. All right. So, this is how this differs, this mechanism differs from the worm and worm wheel. Now, all these mechanisms, that is teeth, they can be cut with the using the module gear. Let us say here this is an example of the module gear, and this module is 1.5 by the way. So, this module gear is used to cut this kind of gears, okay. These gears where the module is 1.5 as well as this gear, okay. Here also it fits in. So, these gears are cut with the module gear. Here if you see, there is another mechanism which is the bevel gear mechanism, and this mechanism is used to transmit the power between the shafts which are at a 90-degree angle. That I already told you while showing the bevel gear. Here if you can see that both can be either driver or a driven. So, here the shaft will be in this way, the gear will be mounted on the shaft, and this gear can be mounted on the shaft like this. So, these two will make an angle of 90 degree. All right. So, here if you rotate this bevel gear will rotate. So, in that case this is driver, this is driven, or if you rotate this bevel gear which is then driver, then this bevel gear also rotates, and this will be in that case the driven gear. All right. So, this is called the bevel gear. Now, how these gears are generated, how these gear teeth are made in case of bevel gear or in case of spar gear, that will be will show you in the milling machine. All right. You can see here there is one mechanism which is called the Geneva mechanism. All right. And the Geneva mechanism is something where the transmission is made intermittently. So, normally the Geneva wheel, it rotates at a constant speed, and this is the driven, then in that case this wheel, Geneva wheel, is the driver wheel, and the Geneva mechanism, this is then the driven wheel. All right. So, in this case, as it is rotating continuously, the pin on the Geneva wheel, it will actually come in contact and enter the groove, and then it will go out. During that, this Geneva mechanism will rotate from one position to another position, and then it will stop. Okay. So, we will show you another Geneva mechanism where it is working in the sense that it is given the drive to the Geneva wheel, and how this mechanism works. So, once again, this is the driver mechanism, driver element, which is the Geneva wheel, and this is the Geneva mechanism, which then as this wheel is rotating continuously, it will get an intermittent motion. So, how it will be, how it works, we will show you in the Geneva mechanism. All right. If you see here, this is the ratchet teeth on the face, okay, and this is the ratchet teeth on the periphery. So, both are ratchet teeth, but this is on the face and this is on the periphery. So, this is the ratchet teeth cutter, all right, and if you can see that this fits in exactly well here, all right, and this is the cutter which is used for cutting the ratchet teeth on the face or on the periphery. So, of course, this is cut with a certain offset, not exactly like this is cut in here, all right, this is made here. So, this is the ratchet teeth cutter, milling cutter, which is used once again for making the ratchet teeth on the face or ratchet teeth on the periphery. So, both are the ratchet. Now, here if you see, this is the chain and the sprocket mechanism, and the chain and sprocket mechanism you must be knowing that because it is used very popularly in the bicycle. This is the driver wheel, where here the pedals are attached, and if you are rotating that, there is a positive drive through the chain between the driver and the driven one, and this on the driven wheel, the shafts, there is a shaft here, and on that shaft the rear wheel of the bicycle is connected. So, as you are pedaling, the torque which you are applying, this is being transmitted through the chain to the sprocket, and through the sprocket it goes to the rear wheel of the bicycle, and the whole bicycle moves. So, this is how the mechanism works. That means, the chain and sprocket. This is the sprocket wheel, this is the bigger wheel, this is the smaller wheel, and this is the chain which connects both the wheels. So, this is the sprocket cutter, all right. This is used, this is a milling cutter, and this is used to cut the sprockets. So, as you can see that this completely matches with the profile of the sprocket here, all right. So, this will be used for cutting the sprocket teeth, all right. This is the milling cutter. Well, as I was telling you about the Geneva mechanism, I would like to demonstrate this Geneva mechanism and how it works. So, this is the Geneva wheel and the pin. This pin rotates continuously, all right, with the help of a motor. This motor is attached here, and while it rotates, this pin enters in the groove of this Geneva mechanism, and then while entering and exiting, this rotates from one position to another position, and then it stops for some times when it completes the other rotation. Let us see this. For example, if we switch on the power, all right, you can see that. So, this pin is entering and exiting. So, when the pin enters and exits, it rotates from one position to another position, and then during the rest of the movement of the pin, this stops, all right. So, as you can see this is rotating continuously, and this rotation is made by the motor which is attached with the shaft of this wheel, and when the pin enters the Geneva mechanism and exit, during that time it rotates from one position to another position. So, let us see how and where it can be actually used. So, when it is rotating continuously on this shaft of the Geneva mechanism, if you have a rotary table, all right, and on the rotary table if you have the assembly mechanisms, for example, in these positions. So, when the pin enters into this groove and exits, it will move from one position to another position, all right. Then during the other part, when it is moving for the rest of the rest along the diameter, then the assembly process will be made, because it is not rotating, it is stationary. So, that is called the dwelling, all right. So, it will be indexing and dwelling with the continuous rotation of the pin. So, this is the advantage of the Geneva mechanism, and this translates the continuous rotation of the driver mechanism to the intermittent motion of the driven mechanism. In this case, this is the driver mechanism, all right, and this is being driven. So, this is the driven mechanism, all right, and this driven mechanism will be rotating intermittently. It will rotate and stops for some times. When the pin completes the other rotation, then again the pin enters to this groove and exiting. During that time, it is rotating from one position to another position. So, this is the advantage of the Geneva mechanism, and this kind of mechanisms are very popular. They are used very popularly in the industry for transmitting the continuous movement to the intermittent motion of the driven mechanism. Well, now we will demonstrate you the functioning of the milling machine. Here we have the horizontal milling machine, because as you can see that this is the axis of the milling cutter, and the axis of the milling cutter is horizontal. So, as I said that if the axis is horizontal, so that milling machine will be called as a horizontal milling machine. Now, in this milling machine, the horizontal milling machine, you can actually mill the surface. That means, you can make a flat surface, you can make grooves, you can make the slots, as well as you can cut the gears, all right. For making the flat surface, the milling cutter will be mounted on in the arbor, and we will show you how the milling cutter can be mounted. In that case, the workpiece has to be mounted on the vise. The vise has to be separately mounted on the table of the milling machine, and that I will show it to you while describing the vertical milling machine, all right. And then the arbor will be tightened with the milling cutter. Here are the spacers. We have seen that arbor separately in the tooling section, and the flat surface grooves, slots, they can be obtained. Now, here while the for cutting the teeth, either it is a spar gear teeth or it is a bevel gear teeth, we use an indexing mechanism, and the indexing mechanism I already told you that indexing mechanism is used for or it is also called the dividing head, meaning that you divide the number depending on the number of teeth, you rotate the blank of the gear at that angle for getting the position for the for cutting the next tooth, all right. So, this is called the dividing head or indexing head. In here, the transmission is given through the worm and worm gear, and the job or the blank will be mounted here on this. So, this is the transmission or the rotation to the blank will be given through the dog carrier with the help of this attachment, which is attached to the dividing head, and this is mounted in this way, and then the job will be mounted somewhere here in between here with the help of the spacers, and this another end will be coming to this, all right, and this will be moved and or on the centers. So, job will be on the centers, we will show it to you now, and the gear can be cut. So, one gear, after cutting one gear, this has to be operated, so that the position for the next gear can be found out, and that can be found out with the help of these plates, and these plates we have already shown to you some of those plates. So, there are 3 plates there, plate 1, plate 2 and plate 3. So, each of these plates has to be selected depending on the number of teeth that you are cutting. Let us say if we have 20 teeth to cut. Okay. So, for that there is a plate which according to our chart, that plate is plate number 1. So, plate number 1 can cut 15, 16, 17, 18, 19 and 20. From 15 to 20 teeth, for cutting 15 to 20 teeth, the plate number 1 has to be selected. Plates are like this, it has the holes here, and that hole has to be, this has to be engaged to one of these holes along the periphery of the wheel, okay, of the plate. And the formula for that is n, that is the number of teeth that you are cutting, divided by 40, and divided by 40 because inside there is a worm and worm gear mechanism, as we said. Through the worm and worm gear mechanism, this rotation is given for the blank. The blank is rotated from one position to another position of the teeth, all right. And if it is worm gear, we will show you how this 1:40 can be obtained. This is the simple mechanism which is inside the indexing or the dividing head. So, here this is the pin, that is the plate that we have shown it to you. Now, the plate is rotated and the axis of this handle is connected to the worm mechanism, worm here, and the worm is connected to the worm gear which has 40 teeth. Okay. So, here the formula will be 40 divided by n. 40 divided by n means that n is the number of teeth that you have to cut. Now, depending on the plate, for example, we have the plate 1 where you have 15, 16, 17, 18, 19 and 20. These are the number of teeth that can be cut using the plate number 1. So, in that case, suppose you are cutting suppose you are cutting 20 teeth. In that case, this will be 40 by n. So, 40 by 20 is 2. That means, it needs a 2 complete rotation of this, so that one tooth will be displaced. Spacing will be one tooth. So, you have to actually cut the next tooth. So, therefore, 2 complete rotation for cutting 20 teeth. Let us say for cutting 18 teeth. In that case, the formula applied is 40 divided by 18, which will be 2 into 4 by 18, and 4 by 18 means the 2 complete rotation. Then out of 18 there are 4 holes, these have to be moved. Okay. So, we will show it to you here in the real mechanism which is attached in the milling machine, and show you how this indexing can be done. So, that when the teeth is cut, when we can get the next position of the tooth to cut. Well, now we are going to show you that using this machine and the dividing head, how we are going to make the bevel gear, the spar gear like this. So, this is the drawing of the spar gear that you can see here. Okay. Here there are number of teeth, let us say 20 we will cut, and this is the side view, or rather the view along the AA section that you can see here. All the dimensions are given here. Now, the blank has been already made, and this blank is fitted here in this arbor. So, accordingly, this outer diameter, so number of teeth, if the number of teeth is 20, and let us say module we will take as 1.5, okay, this is the module as 1.5, then there is a formula that the outer diameter will be m into n plus 2. M is the module and n is the number of teeth. So, number of teeth will be 20. 20 plus 2 is 22 into m is the module 1.5, which makes it 33. So, the outer diameter has to be 33 millimeter, which has been selected, and this is the blank which is made in the lathe. Okay. So, it is already turned and the blank is mounted on this mandrel. Now, the rod diameter means which goes into inside of this blank, which is the inside diameter of the blank. Inside diameter of the blank has been given as the 12.7. Let us say we have selected 12.7 millimeter, and the depth of cut formula, that how the depth of cut will be given, depth of cut for the tool, that is a milling cutter. This formula is given as the 2.157 into module. This is the standard formula for the spar gears. So, 2.157 into module is 1.5 selected. So, that will make you 3.24. So, therefore, 3.24 depth of cut has to be given to the tool for making the 20 teeth here along the periphery of this blank. Indexing formula I already told you, that is 40 by n, n is 20. So, 40 by 20 is equal to 2. So, therefore, it will be 2 complete rotation of this plate that will make the indexing, that means from one tooth to another tooth. How to space the one tooth and the next tooth when you will be cutting, it has to be moved 2 complete rotation, because this is 40 by n, n is the number of teeth which is 20. So, 40 by 20 is 2, and then the tap hole size is 5.2 millimeter drill and 1 by 4 inch of the tapping. So, these are selected so that all the other operations are completed. Now, Mr. Aman Singh will show you how to mount the mandrel on the between the centers, and then how to mount the milling cutter on the arbor, and then how to cut the gear and how to index for cutting the next tooth. So, in this display you can see the different milling cutters. Okay. So, these are all the standard milling cutters, and we have to select one of these depending on the specification which are given. For example, this milling cutter is used for cutting 135 number of teeth 135 or more. For example, for cutting the rack. Okay. In rack, you know that number of teeth will be much more, okay, depending on the length. So, there this kind of milling cutters are used for cutting number of teeth 135 or more. All right. This milling cutter, this can be used for cutting 55 to 134 number of teeth. All right. Number 3, so this is number 2, these are all standard milling cutters as I said. So, number 3 is for cutting from 35 to 54 number of teeth. This milling cutter for cutting 26 to 34, this milling cutter for 21 to 25, and this for 17 to 20, this for 14 to 16, and this milling cutter can be used for cutting from 12 to 13 number of teeth. Now, this is based on the pressure angle, okay, because 2 teeth can be teeth of the milling cutters, both milling cutters have to meet. So, if the pressure angle is different, in that case of course, there will be different. So, all the milling or all the gears, for example, where you will have the 20 teeth. So, we are going to cut 20 teeth. So, this is the milling cutter that has to be selected for cutting the gear, spar gear with the 20 teeth. All right. Meaning that if you are cutting 2 spar gears of 20 teeth, for both you have to use this milling cutter, otherwise they are not going to match, because their pressure angle will be different if you use the other milling cutters. So, this is the basis based on which the one or the other milling cutters are used, that is the pressure angle which is the basis for that. So, we will be using this milling cutter which has to be mounted on the arbor of the milling machine, that Mr. Aman Singh will be showing to you. Well, here Mr. Srinivaslu, he is demonstrating how the milling cutter number 6 we said, because this is the milling cutter that has to be used for cutting 20 teeth. So, how the arbor can be removed and how the milling cutter can be mounted on the arbor. Okay, Mr. Srinivaslu. Here this is to be removed. This is the arbor support. And these are the spacers which have to be removed for mounting the milling cutter. Now, the milling cutter has to be mounted on the key. Okay, key is there, you can see that, and key, yeah, here it is the this will be mounted on the key. Okay. Yeah. So, this will be on this side, because it will be
forward direction,
this will be down milling,
up milling.
this will be up milling, sorry, up milling.
Cannot go down milling.
Okay, this will be up milling, yes. So, as you understand that up milling, what I said is that you mount it. Up milling means the rotation of the milling cutter and the rotation of this the blank will be opposite. So, this is normally called the up milling, and here we normally do the up milling, because down milling is, as you understand, that this is not appropriate for this situation. That I will describe in details in the lecture classes. Aman, that so this is the spacer on the arbor. And then finally the nut has to be put on the arbor. And this is the support. When it is tightened, as you can see that the milling cutter is rigidly fixed on the arbor. So, there will be no movement, relative movement between the arbor and the milling cutter. Arbor will be moving along with the milling cutter with the same speed, and arbor is mounted on the spindle of the milling cutter. That on the milling cutter table is the vise on which the part will be, or the blank will be mounted between the centers. You can see that there is a dead center there, and here is the job which has been mounted. This is the dog carrier. The dog carrier is attached to that arbor or mandrel on which the workpiece is mounted, and the workpiece is here. This is the workpiece, all right, on which the gear will be, or gear teeth will be cut. This, the whole attachment with the dog carrier is mounted between the centers. One center, one end will be attached to the dividing head, and another is on that vise. Now, this vise is to be fixed on the milling cutter table, and it can be fixed only when the dead center is attached to the arbor, to the mandrel with the workpiece. Well, they are tightened. Okay, it is tightened. All right. So, now it is ready for cutting the gear. All right.
Yes,
Now, you have to set the plate of the indexing device or dividing head. So, I will remind you once more that there will be 20 teeth to cut. So, here this is the plate on which you can see that these are along the periphery there are different number of holes. Okay. So, since we have to rotate 2 complete rotations, so this pin can be attached to any of the holes, but overall the disc has to be rotated 2 complete rotations, so that the blank rotates by 1 tooth, all right. Because as we said that the formula is 40 by n and the n in our case is 20. So, therefore, 40 by 20 is 2. So, this 2 is meaning that 2 complete rotation of the plate, so that 1 rotation or rotation by 1 tooth can be made for the workpiece. Okay. So, before we start cutting the gear teeth, first of all this has to be centered, and centered because the milling cutter has to be centered, because this is a straight teeth. Now, if it is not centered, as you understand, then the offset will be made, and then the accuracy of the gear will be lost. For that, here it has to be made in the 0, all right. That means, in this scale if it is 0, so it is exactly at the center, then it will be touching the workpiece here. When it is touching, this has to be made as 0, that is the 0 point here. Then from that 0 point, here it will be fixed somewhere, which will be 0, indicating 0 point, and then 2 complete rotation has to be made for the next tooth to cut. Okay. Now, the machine is on. You are touching touching the milling cutter with the workpiece, which will indicate, yeah, it is exactly touching. So, this will indicate the 0 position. Yeah, I will tell you, make it. Yeah, now it is the 0 there, as I said. Then here. So, it is the 0 position. According to the 0 position, this has been fixed. Okay. Yeah.
Now we can do that.
Yeah.
Now we are going for depth of cut 3.24.
So, 3.24 is the depth of cut that we have calculated.
1
So,
mm.
that depth of cut is given by this scale. Okay. That would be in 1 pass. 3.24. Okay.
Depth is given.
3.24 is the millimeter, which is the depth of cut. See, this much material will be removed by the milling cutter.
Now we can go for the cut. Switch on the coolant.
Coolant.
Yes.
Now the coolant is on,
Now we are cutting.
and the gear cutting will take place. See, the feed is given manually, and as you can see, the feed is given. Feed means the movement of the table along with the workpiece, so that the full length of the gear can be cut. Okay. Good. One tooth is completed. You can stop. You can stop the.
Now it is full will come back
Yes.
to the original position.
Yes.
At original position, then loosen this one and go for indexing 2 revolutions.
Yeah. So we have to now rotate twice this plate
Twice.
for the next tooth.
Next two. 1 revolution and then second revolution. Keep this one in position.
So that means with the two complete revolution of the plate, the gear blank will be moving from one position of the tooth to the next position of the tooth, as I have shown it to you in the worm and worm gear. Okay. Worm and worm gear, I will remind you that that is inside the indexing mechanism, the dividing head. So now it is the next position. The blank, as you can see, is in the next position, and the next tooth can be cut. So that is the second tooth that has been cut, and when taking the, if we rotate the same way, again 2 complete rotation of this plate, then the position for the third tooth will come and the third tooth will be cut. So, if you continue doing that, that means after the second tooth you make a complete rotation, 2 rotations of this plate. Okay. So, 2 complete rotation of the plate will move from one position to the next position and the third tooth will be cut. And you continue doing that, in that case your complete product, finished product will be like this. So, this is the gear that has been made here similarly that we were demonstrating, and there are 20 teeth according to the drawing that I have shown it to you, and here there is a threaded hole. After that, after the drilling and the tapping, this hole can be made. There is a central hole here that has already been made earlier, and this is the complete finished product that can be used. You have so far seen the gear cutting process, gear cutting technology we have described in details, and that was done on a horizontal milling machine. So, in there we have told you that how to make those calculations. I have also shown it to you in a PowerPoint presentation, and the entire process, entire technology has been described and has been demonstrated to you. Today, we will show you the technology of the gear cutting for the bevel gear. So, we have shown you earlier what is the difference between the straight gear or the spar gear and the bevel gear. So, today we will show you how these bevel gears are cut, and then you will understand that what is the difference in this technology. So, before that I would like to tell you that for the bevel gear we will be using this drawing, and this has been shown to you in the PowerPoint presentation as well. So, you can see the all the dimensions here, what kind of dimensions or what kind of measurements that you can take for the bevel gear, and we have to make a small calculation before the teeth cutting, like in the case of the spar gear. First of all, we have to find out that what is the shaft angle. Shaft angle means that when the bevel gears are connected with each other, 2 bevel gears are connected with each other. So, the shafts normally, as I said to you, that they make an angle of 90 degree, okay, if they are normal bevel gears, but there are bevel gears where the shafts may make an angle which is different from the 90 degree angle. So, that angle is called the shaft angle. Module is M, pressure angle is alpha, and then the number of teeth. So, number of teeth we are deciding. So, here for example, the number of teeth that we have decided is 30. If you have seen earlier that for the spar gear we have demonstrated for a spar gear of 20 number of teeth. So, here we are actually demonstrating the number of teeth is equal to 30 that we have decided. Now, the pitch diameter formula. So, to find out the pitch circle diameter you understand. So, this to find out we have a formula of Z into M. So, this is the number of teeth, and that has to be multiplied by the module is M. So, in this case for the pinion our D1 is 45, and for the gear the D2 is also 45, because we are making as I said the number of teeth 30 and module is 1.5. So, that makes it 45. Now, the pitch cone angle, we will show you the pitch cone angle at in the drawing, and this can be found out with a formula of tan inverse of sine angle, some angle, and that angle is the shaft angle divided by Z2 by Z1 plus cos of the shaft angle. So, there is a particular formula that can be derived, and that formula can be used for to find out the pitch cone angle, and in our case the pitch cone angle has come out to be 45 degree. Now, the cone distance, this is given by a formula, that is d 2 divided by 2 of the sine of the angle. So, that has become 31.82 degree. Face width, that should be less than some value, okay, or 10 meter, less than 3 or 10. So, this has become 10.6, this is the face width. Also, the face width you can decide, for example, you want the face width to be this. So, there is a recommendation in practice that face width cannot be less than something and more than something. So, that is what we said to you. Addendum is 1.5, dedendum is 1.875. You know that the dedendum concept, that addendum is that difference between the maximum diameter and the p circle diameter, whereas the dedendum is the difference between p circle diameter and the lower diameter, okay, minimum diameter. Then similarly, the dedendum angle, addendum angle, outer cone angle. So, for everything there is a formula, and according to that formula, for example, in case of addendum it is 1 m. So, which is 1.5, m stands for module. Dedendum is similarly 1.25 module. So, that has become 1.875, module become 1.5, module being 1.5. So, and so on. So, we have to make all those calculations and get them ready, the values we have to get them ready to set the machine. Now, here we have the horizontal milling machine again. So, similar to that machine, although this machine is different from the one that we have seen earlier for the spar gear cutting. So, here we have the spindle, on the spindle we have the arbor, and on the arbor we have to fit the milling cutter. The milling cutter that we will be using will be from that table, from that chart that you have seen, from where we have selected the milling cutter for cutting 20 gears. So, today we will be selecting a milling cutter for cutting 30 gears. So, from that table we will select the particular milling cutter. That will be mounted on this arbor with the help of the spacers. Finally, it will be tightened by this nut, and then we have the dividing head, and you know the principle of the dividing head, we have shown it to you for spar gear cutting. So, accordingly we will be using the dividing head with the help of the the plates, okay, and the principle remains the same. So, here only thing is that now the same formula will be used, that is 40 by n, that is what we said, that how many rounds we have to rotate for this. So, for example, for cutting 30 gears it will be 40 by 30. So, this will be 40 by 30 means 1 and remaining will be 1/3. So, 1/3 can be said to be 6 by 18. So, suppose we have 18 holes in the on the periphery, we selected the 18 holes piece circle diameter. Out of the 18 holes we have to move to 6 holes. So, one full rotation and another 6 holes with that 18 hole piece circle diameter. So, this principle remains the same as in case of the spar gear cutting, all right. So, once again, for example, for cutting 30 gears it will be same formula will be used, 40 by n. So, it will be 40 by 30, which is 1 and 1 by 3. So, 1 by 3 we are taking as 6 by 18, and therefore, the 6 by 18 does mean that you take the plate, and when there are 18 holes, out of those 18 holes where the pin is set to the piece circle diameter, where there are 18 holes along the diameter, and out of those 18 holes you select 6 holes and move further to that that angle. So, that will make you the indexing for cutting 30 gears in the 30 bevel gears. So, that we will be showing. So, let me tell you a little bit about this machine. We have the machine bed. On the bed we have the dividing head. Here we have the support for the longer jobs. So, the workpiece will be mounted on this, okay, on the dividing head, and it has a 3 jaw chuck. On the 3 jaw chuck we are mounting this. So, before we start cutting gear, we have to make the blank on the in the turning lathe. So, because all these things have to be turned, these surfaces have to be turned, and then on this surface, in the conical surface, the bevel gear teeth have to be cut. So, in this horizontal milling machine, we have the handles for the cross feed, all right. This is for making the table up and down, and here is one more handle. You can see that this is for the longitudinal feed. So, the mechanism is similar, and this machine actually has been taken as a horizontal milling machine for cutting the bevel gear. So, we have Mr. Srinivaslu, and he is going to operate the machine, and he is going to cut the bevel gear and show you the entire cutting process. All right, Mr. Srinivaslu, please. Yeah, this is the gear that we have, this is the milling cutter that we have selected. If you remember that we have told you that that is for cutting 30 gears, okay, and that has to be mounted on this arbor. Yeah. First this has to be removed.
Arbor support.
Yeah, this is familiar to you because earlier also for the gear cutting, for the spar gear cutting, we have shown you the similar process, that how this gear has to be, how this milling cutter has to be mounted. These are the spacers, they are being removed from the arbor. Yeah, so then with the help of the key, okay, and this is the key way. In this key way, the key has to be set, and this key, half of that will be inserted in the arbor, keyhole of the arbor. Okay, so here is the key. Half of that key has gone into the key slot of the arbor, and half of it has gone to the milling cutter. So, the milling cutter is now rigidly fixed with the arbor, meaning that it cannot move with respect to the milling cutter, it cannot rotate with respect to the with respect to the arbor, but it can move axially. So, to stop that movement axially, we have the spacers. These spacers will prevent the axial movement of the milling cutter. So, now when we have the spacers, enough number of spacers, and tighten that with the nut here. So, in that case, the milling cutter is rigidly fixed, it cannot have any kind of relative movement between the milling cutter and the arbor. That is the basic purpose of it. All these are spacers. Yeah, so this will be tightened, and then the support will be held here. Yeah. Do it. Yes. Okay. Cutter is fixed now.
Now RPM.
Yes. Now you have to select the RPM. So, a certain RPM has to be selected because that on that has been determined by the calculation, and here we have the 114. Okay. This is the RPM of the spindle of the arbor. Yes.
Now we are set.
Yeah. Now we have to set the
Cutting
blank and the cutting angle. Okay.
Root cone angle.
Yeah. So, first of all, the root cone angle, and the root cone angle, as I said, has been calculated, and it has been found out to be 41.63 degree. We have you can see that here there is a dial, and that dial is graduated. So, using this graduation of the dial, we can actually set that particular angle, which will be as a root cone angle.
41.6.
41.63, yeah.
So, the least count is 1 degree.
Yeah.
So, we can go 40.
Wow. So, now it is this angle is set at an angle of 41.63, which is the root cone angle, because at that angle the teeth will be cut on the bevel gear teeth will be cut. Now, it is being tightened and it will remain at this angle. Okay. So, in before we start cutting the bevel gear, we have actually with the help of these handles of the longitudinal feed making the table up and down. So, you can see that the gear is almost touching the blank. Now, we have to fix the rotation, how many rotations for indexing. Okay. So, this is the indexing mechanism. In this indexing mechanism, we have to fix the number of rotations, how many numbers. As I said that will be 1 and 1 by 3, 1 by 3 is 1 and the 6 of 6 by 18. So, that means 1 full rotation and the 6 of these holes out of 18 holes. Okay. So, you set the 0
and make 6 holes. You can loosen the sector.
This is just for convenience of moving that. So, this is the sector arm, that sector arm has been set in a position where there are 6 holes.
So, we can count 1, 2, 3, 4, 5 and 6.
Yeah. So, it is set at the 6th hole and then it will be fixed. That is the fixing of the sector, which is now set at 6 holes, 6th hole out of 18. Yeah. So, now it will be for indexing, we know that we can rotate one complete rotation and those 6 holes where that sector is fixed. So, up to that sector it can go. Okay.
Now, we are going to touch on the top surface of the bevel.
So, you will start the machine.
Start the machine. And with the vertical movement, we slightly touch on the top surface of the gear.
So, now with the help of the handle which will lift up the workpiece which is mounted on the dividing head. So, the it is brought to the contact of with the milling cutter.
Now it is touching on the top.
It is touching the top diameter, top surface of the workpiece.
Now we are going to give the depth of cut 3.24. So, we can set here 0, depth of cut 0.
So, the depth of cut is now has to be given
By the up and down movement. So, we can give 6 2/3 with 3.24 depth.
Okay.
One complete revolution, 1 mm in the upward movement. So, we can make 3 revolutions. And 3 complete revolutions, and then we can do the 2 point. Yes, the depth is given. Now we can do the longitudinal movement.
So, that depth which he has given, that depth has been decided by us. Okay. So, you can decide what should be the depth of cut according to the requirement of the gear that you are cutting, where the gear will be working. Okay. So, now it is in the automatic mode and according to the depth that has been given, the gear will the milling cutter will remove the material and cut one tooth on the blank.
We can do the
Yeah, you can see that the chip is being removed. Well, one tooth has been cut and the cable is being retracted, that is the dividing head along with the workpiece has been retracted from the milling cutter. And then the indexing plate will be used for indexing, that is to come to the position where we have to cut the next tooth. And for that we will be rotating one complete revolution of the disc of the plate, and the 6 holes as we said out of those 18 holes, that will make you 1 by 3. So, it will be 1 and 1 by 3, that is 30 divided by 40. 30 teeth you are cutting, and the formula is the same as in case of spar gear cutting, which is n by 40 by n. So, it will be 40 by 30, which is 1 and 1 by 3. So, this is the gear. Now, the blank is in the next position for ready to cut the next tooth, and now the milling cutter has started removing material in the position where it is the next tooth is being fabricated. Well, both the teeth have been cut. Stop. Similarly, when all the teeth will be cut and the cutting process will be the same, meaning that when one tooth is cut, then you have to use the indexing head to rotate to come to the next position, then again rotate the same way, that means one complete rotation of the plate, and 6 holes out of those 18 holes, which will make you 40 divided by 30, because 30 teeth you are cutting, and this is the final product that you can see that has been made fabricated in this machine. So, all the 30 teeth are being fabricated, and this is the complete bevel gear that was required as per the drawing that has been given. Thank you for your attention.